Welcome! Today we're going to talk a little bit about troubleshooting and analyzing a faulty boot process on a Model 1 Sega CD. I'm going to cover kind of just the basics of how the Sega CD is set up, some early simpler troubleshooting steps, and then we'll look at it here on this HP logic analyzer. Hook up all the probes to the Genesis CPU and pull it up on the analyzer so we can see how the analyzer decodes the assembly language that's running off the Sega CD at boot up, and we can use that to see where the code is crashing and where the fault is. So let me say up front that I'm not an expert by any means. I don't have any formal education on electrical engineering, no education in computer engineering or design. My background's really in software, so I really just figure this stuff as I go along from reading how other people do things and watching how other people fix things on YouTube videos. So, you know, I can't guarantee that everything I say here is the best way to do things, but I can at least say that, you know, it's as accurate as I can ascertain it to be. Okay, so let's jump into it. So we've got a Model 2 Sega Genesis over here. It's the Model 1 Sega CD board. This interconnector board goes between the expansion connector on the Genesis to the parallel connector here on the Sega CD, and then this is the power board that powers the Sega CD. We'll say that with a lot of Sega CDs that don't power up, the common fault is usually a fuse. In this case, I laid the fuse down sideways just because of some damage on the underside of the board right here. This fuse is a common power problem. This transistor here, I think it's a relay, transistor or relay. This takes care of switching the whole power circuit on when it receives a power on signal from the Genesis. Those fail sometimes, but not as much as a relay. And then there is a diode. Let's see, where is that diode? Oh, right here. Yeah, then there's a little diode here as well. Usually those three are your main troublemakers when it comes to, failure of the power board. There's also a voltage regulator over here that takes the 9-volt input from the main power adapter and then adapts it down to 5 volts before passing it on to the Sega CD. And it's not as common for these to go out, but it does sometimes happen. What you were generally looking for to make sure that the whole circuit is operational is there's 3 legs on this transformer. The middle leg is negative, and one of the legs receives 9 volts from the input over here on the left, and when you turn the Genesis on, you should read 5 volts coming out of here. And if you don't read 5 volts, then it's not switching on over here from the transformer on the left. If you don't read the 5 volts. If you don't read 9 volts, then there's something else wrong, probably with the main fuse itself. Now there's also a secondary fuse on right here that protects the power as it comes in off this connector that connects the power board to the Sega CD. So again, if you are having a no power problem, you would want to check this ribbon cable, check this fuse. If you take a multimeter with the Genesis turned on and everything connected, and put your positive on here and your negative on the ground plane around the outside, you should get 5 volts off that fuse if the board's receiving power from the voltage regulator. So, okay, so that's simple stuff as far as looking at power goes. Model 1 Sega CDs use these surface mount capacitors. Well, that's surface mount, that's a through hole, and but most of the caps are surface mount. Those surface mount caps leak, and when they do, they leak with age. You know, when they get to be 20, 30 years old, they leak, and when they do, they kind of vent their electrolytic fluid innards out onto the board underneath, and they can eat through traces. And when those traces get damaged, then that causes breaks in the circuits and then things don't work anymore. And again, that is a very common cause of failure on these Model 1 Sega CDs. So if you haven't had cap replacements done yet, definitely #1 priority, get it recapped ASAP. This particular Model 1 board, I was fortunate to get it and recap it before those caps leaked, and so I didn't end up having to do any trace repairs. One thing I did do is I removed the original rechargeable watch battery that maintains the backup memory right there and put in a coin cell holder, and then when I put this Sega CD back together, I'll just put a rechargeable coin cell in right there. Alright, let's take a look at the Sega CD mainboard itself here. So, as with a lot of retro electronics, these things are kind of laid out according to, functions. Different clumps of parts have different functions in the whole system. So, with the Sega CD, this EEPROM chip that holds the BIOS code, the boot code. Those of you familiar with Sega CD know when you turn it on, you get a cool music, splashy earth background, spinning logos, that kind of thing. All that boots off of here. Now this is the Sega CD's Motorola 68000 CPU, but in this case, this EEPROM code does not execute directly off of the CPU here. Instead, the Genesis reads it just like a cartridge. As far as it's concerned, this chip is just like starting up a normal game cartridge. And so these pins appear to the Genesis more or less like a normal cartridge slot. And so the Genesis actually reads the code off of here, and then the Genesis in turn goes and does some setup operations on the board and then boots up the secondary CPU. But we'll cover that a little bit more later. But main things to know is, so we got the EEPROM, that's the BIOS, boots that up. On some Sega CDs, like this one, it's a flash EEPROM inside a socket, and other systems it's a ROM inside a, it's just a mask ROM. 68,000 slave CPU. This is the DRAM, 4 megabits of DRAM that's assigned to the slave CPU. And then this is the PCM audio chip, adds additional audio channels. These two chips are memory for the audio, so if you have audio problems, like half the notes are cutting out on that Sega CD splash screen, it's probably a problem with the connections on these two chips. This chip here is the CD-ROM controller. It goes to the connector right here that goes out to the CD-ROM drive, and these two memory chips are storage memory for the CD-ROM data. And over here on the right, this large Sega chip runs the show. Sega calls it the Mega CD engine. It's basically a large custom chip that incorporates memory controller, graphics processors, and all kinds of bits and pieces that are really, besides the CPU, this is really the guts of the Sega CD. Basically, if this chip goes out, then the board is pretty much gone, because all these other parts can be, except maybe this Sega PCM, but all the rest of this are off-the-shelf parts so you can buy replacements for, but not the custom large Sega chip. It is common. It's a surface mount chip with a lot of very little legs. It is possible sometimes for the solder to break and for some of those pins to lift up a little bit. So again, we'll talk a little bit more about continuity and everything later. But so if you're experiencing some problems, and you're good with surface mount soldering work, you may want to run around the edge and resolder the chip here. Okay, a little bit more here. So these two long chips are graphics memory for the GPU inside the custom chip here. And this is important. This is the clock generator. Generates a 50 megahertz clock that the whole system clocks off of. Again, if you're having problems, you'd want to check and make sure that that's generating a signal, because if that clock goes out, then everything will appear dead. This is the backup memory chip. It's powered by the watch battery and stores the your save game data. And then finally, we've got a few little ICs here, over here, and right here that handle distributing those clock signals out to different areas of the board. So that's kind of just a general rundown of how this board is set up. Let's go ahead and talk a little bit about troubleshooting. Okay, so let's talk about some basic troubleshooting here on this board. So if you have a Sega CD that doesn't start up, and you've replaced the caps, replacing the caps first is the most important thing. You're going to want to go around and check some traces. So every cap provides power to the chips next to it, more or less. So these two surface mount capacitors provide power to these chips in this area. This surface mount here provides power to the PCM and to the EEPROM. This one handles power to here, this one handles power to here, this one handles power to the CPU, and this one handles the custom, these two handle the graphics chips, etc. So what you're going to want to do with each of these is you can look up the schematics on all these chips. If you go to Console 5, they've got a Wiki which has schematics to all these things. In fact, let me pull one up here. Okay, I've got some schematics here, so ignore my handwriting. That's to do with some other troubleshooting I'm doing. But like for the work RAM, the 4 megabit work RAM right here, the VCC pin is your power supply pin, and likewise this is with one of the graphics memory chips. There's two 1 megabit graphics memory chips, and VCC is your power pin here. So what you should be able to do is you can set a multimeter to continuity mode. You want to touch it to the side of the cap that doesn't have the black stripe, because you want black stripe's ground, white side is positive, and you should read continuity between the white side of the cap to the VCC point on the adjacent chip. So you want to verify that for each of them. So that's for a continuity test. If the board is getting powered, you have your multimeter on, you should be reading 5 volts of current to the power pin on each component. So that's some basic troubleshooting. Another thing is you want to verify all the pins on this connector. Again, let me get a diagram here. Okay, this is the schematic from the Sega CD service manual that's hosted on the Console 5 website. Again, ignore my handwriting, that's from some other stuff. But if you look down here on the connector, you can see we've got the A side starting at A1 down to A30, and then the B side going from B1 to B30, and it maps out where all these lines go to. And there'll be a few like NC that are not connected, or this 9-volt line that doesn't go to anything. Those ones you won't get any kind of continuity reading on with a multimeter, so those ones are okay, but all these other ones you should be able to verify continuity between their point on the board and their destination. So one thing to note here is it's printed in a little writing on the board, B1 and B30. So that's the lower half of the connector, B1 to B30. And then if we flip it over here, you can see we've got A1 to A30 there. And so again, that will be the top side of the connector. And a lot of these pins end up going into buses, so we can see the address lines here, A4. We know their address, or sorry, these are data lines, VD. D is data, VA, those are address lines. That's all for the EEPROM that boots up the Sega CD. So verifying those lines is important. And again, those all end up leading into Genesis, and the Genesis boots the system off of them. So we've got 16 data lines here, numbered 0 to 16, and then we've got address lines here labeled 1 to 17 with a ground in between. I don't know why they started at 1 instead of 0 there like they did with the data lines, but anyway, you want to verify those, and there's a few other ones in here that are control signals. But anyway, like I was saying, when you have lines that go into a common line here, that's basically a bus. And so if we look at these data lines and trace the line over, we can see it goes to VD 0 to 15, and likewise the address lines are VA 0 to 17. And I ended up writing over that, but that's MC for memory control. You can see those three lines are all different collections of buses. So those are address lines going to the VA, and then these are memory control lines right here for those three, and that set of four right there. So those collect. And so when they go off the page here, that means that it's going to another page of the schematic. So let me swap here. Okay, here's another page of the schematic. In this case, it's for the large Sega CD engine, the large custom chip there in the lower right corner of the board. And if we look, there's our VD lines. Those were our data lines. And we can see which pins they go to on that Sega CD chip. So, those are the address lines. VA lines are here. VD lines are right here. And then the MC is the memory control, and those are here. And so you can look that, VA 0, for example, oh, that's right, they started addressing at 1, I don't know why, but okay, so VA1 is pin 171 on the Mega CD chip. And so, again, if we come over here, it starts numbering right down here at the bottom where that little pointing arrow is. We got 1 to 52, 53 to 104, 105 to 164? What's that say? 156, sorry, okay. So 105 to 156, and then 157 to the last one, 208. And so you can kind of count them out. So again, we're looking for 171. And so if we go to 157, the dot is then shows we're at 160, 165, 170. So then one pin past that dot is 171. And I don't have a multimeter here, but you should be able to touch your set your multimeter on continuity mode, touch one probe to that pin, and then the other one to that was VA1. And VA1 on the connector was, come on, focus up here. VA1, okay. VA1, line VA1 is B3, so that means if we counted from the starting here, 1, 2, 3, that third pin from the right there would beep for continuity on 171 down there if the trace is intact. So it's a little tedious, but you're going to want to go through all 60 pins on this edge connector and verify continuity for all of those, because if any of them are broken, then they're going to have to be repaired. And again, they can break when the caps leak and cause damage to the board. Okay, so besides those edge connections, the other one that can cause problems for it to not boot up will be the connections from to this DRAM chip right here, the work RAM. That work RAM is basically this first Genesis reads the EEPROM at boot up, gets some instructions, then it starts filling this chip up, and then it kick-starts this slave 68,000 processor, and the 68,000 starts reading from that chip. So again, if it's not booting up, it could be a problem with those edge connections, it could be a problem with this, there could be a problem with the DRAM. And again, if we go to the schematics, let's see. Okay, this is another page of the schematics. Now, here's a place where it's a little trickier to work with. The reason why is these schematics are from the original first revision of the Japanese Mega CD, and this one is a, maybe you can see it written sideways there. This is a export board, Mega CD export board. So it used to be that they used 4 individual 1 meg chips for the DRAM work memory, but for the export version they consolidated it down to 1 4 meg chip. So what you end up having to do is, rather than following, you can't follow the traces off these chips because it's a different kind of chip. You'll have to do it the hard way. If you look closely, hopefully those show up, you can see the individual traces coming off each pin. you'll need to trace those lines wherever they lead on the board and check them again between with a continuity setting on the multimeter between the source pin and wherever their destination is, pin by pin for each line. If in some cases the trace might go to a via, that looks like these little round circles here. A via is where a signal hops to the opposite side of the board. A lot of the time it was just so they could make all the circuitry fit. There wasn't enough room for everything on one side, so they go to the other side. So if it goes to a via, you got to trace the via. Use your continuity tester to put one probe on one side of the via, put it on the opposite side, make sure the continuity carries through, trace it on the back side, and then probably end up taking a via back to the front side again. But one way or another, all of these DRAM pins should have continuity between their source here and a destination. Okay, let's talk real briefly about the boot ROM itself, the EEPROM that holds the code for the BIOS. It is possible for these chips to fail or get corrupted. If it's a socketed EEPROM like this, you can just kind of carefully pry this EEPROM out with a flat-headed screwdriver, a little bit on this side, a little bit on this side, until it lifts up out of the socket. Then you can use a chip programmer, like I've got a Schematics 2 right here, and basically you just go and use it to dump the chip and compare the code in the chip you dumped to another dump of the BIOS file that you can download off the internet somewhere, and you just want to make sure they verify. There is region-free BIOSes available out there. If you want, you can erase this EEPROM by peeling the Sega sticker off of there and putting it in a UV eraser for half an hour to erase the chip, and then program it with a new BIOS. Or you can just buy a fresh ROM and do the same thing. But again, if the BIOS is corrupt, then it won't read correctly and you'll have a problem. I have seen on some Mega CDs where this cap leaks and it damages traces here. Actually, it looks like I did end up having a repair on this one. I forgot about that. But in this case, when this leaked, it damaged these traces going out to the EEPROM right here, and so I did have to do some repairs. You can see some evidence from that there. Okay, so let's say you've gone through and you've verified continuity on everything. You've pulled out the EEPROM, checked it, dumped its code and checked it. You know you've got proper code on here. And you know you're getting power to all your components because you checked for continuity and you checked for voltage with VCC line versus ground on each of the components. Still doesn't boot up. What do you do? Well, your next step would be to start taking a look at it with either a logic probe or an oscilloscope. Rather than just showing pure voltage, a logic probe will tell you what the circuit's doing. You know, this is all binary logic, so every signal will either be high or low. So it's low if the pin is grounded, it's high if it's showing voltage. These boards are all TTL, so I think that voltage is something like 2.5 volts, something like that. Doesn't matter for our purposes. Anyway, get a logic probe, set it to TTL. You need to hook it up to power. It has to be powered off the board itself. What I usually like to do is I'll clip the positive end onto the tip of the fuse, the power fuse right here, and then just hook the negative up to the ground over here in the corner. And what you want to start doing is you just want to, again, check against the schematics. You want to start tapping. I won't be demonstrating this live, but basically you tap against each of the address pins, you tap against the data pins, and what should be happening is it should be flickering up and down between high and low. You know, just rapid flickering back and forth. If it just holds high or it just holds low, that means the system is stalled. Nothing's happening. So, you know, you've still got a problem. If you get no reading at all, it doesn't read high or low, but you get nothing, it's like you weren't touching it to the pin at all, that pin's disconnected. It's floating, and that means that you probably have a break in the circuit that you need to repair. But for your basic troubleshooting, you're going to look at that boot ROM diagram. Okay, so I got the schematics here, and basically all your memory components are going to have address lines, and they're going to have data lines, and they're going to have control lines, and power, which is VCC, and ground. And the behavior you're looking for is VCC should hold high on the probe, because that's your 5-volt in. Ground should always hold low, because that's, that sends it to ground. So if VCC or ground aren't showing a reading on the probe, then that's a broken trace and it needs to be fixed. Then address lines should be flickering back and forth. They should be flickering high and low. Data lines should be flickering back and forth. And then finally the control lines, the LCAS, UCAS, WE, RAS lines. Anything that's not an A line or a D line or a power line should be flickering as well. Now, what can be a clue to a failure is if address lines are flickering and control lines are flickering, but data lines are not. That means the chip has died internally and it's not putting data out. Sometimes you're lucky and it'll be an easy fault like that. But basically, if so you're going to check on your main RAM, you're going to check on your the video RAM chips, check on your sound RAM chips. Now again, that's depending on the fault you're having. If you're getting graphics corruption, check your video RAM. If you're getting sound corruption, check your sound RAM. If you're having problems with the CD decode SRAM, which are those chips down here in the corner, it's probably just going to crash because that's your CD data. Although if you're playing an FMV game, that might exhibit itself in graphics artifacts. But again, we're looking at boot problems where it just won't boot up. So you're really going to just be looking at that boot ROM and checking those address lines and the data lines for activity when you probe it with this. So if they're just held, then you either have a failure or it's crashed. And as you'll be seeing with the faulty board I've got, it's crashing. It reads activity for about a quarter second, and then just suddenly all the pins go to being held high, and it's because the Genesis CPU crashes. Okay, so that brings us to this. This is the next level. So let's say you've done everything I've set up till now. You verify all your traces, you verified your power, everything seems to be good, you got fresh caps in place, but it still isn't boot you checked your boot EEPROM for valid code, and that's good. Still doesn't boot. What do we do next? That's when you have to start getting into the complicated stuff. So a logic analyzer basically acts like a logic probe, where a logic probe watches one line at a time and flickers up and down and shows you what it's doing for whatever line you've got it held to. A logic analyzer does the same thing for multiple lines at once. So if you go shopping, on eBay, you'll find these inexpensive logic analyzers that are USB and plug into a computer and run of software. You can see this one has 8 channels, labeled 0 to 7 plus some grounds. And so what you can do is you can run probes off of this and connect it to something like the DRAM or maybe to the address lines on the BIOS chip, and this will show you their activity over time, and you might be able to get something out of that. But to be honest, these new logic analyzers are really designed to work with modern electronics hardware, like Arduinos, Raspberry Pis, hobbyist projects, where all the debugging, they have a dedicated JTAG connector that you can use, and it sends debugging data to these lines as a serial data stream. That doesn't work with old equipment. There was no standard for debugging that back then. You need something with a lot more channels, and so in this case, we're hooked up into the Genesis main CPU itself because we want to read what code is coming off of the Sega CD and finding out where it crashes during the boot process. And so that brings us to this old granddaddy from the 90s, a Hewlett-Packard 16500 logic analysis system. Okay, so what's the difference between this 90s behemoth versus a modern Chinese logic analyzer? Big difference is, of course, this is a self-contained unit. You don't have to hook it up to a computer to have it run the code to trace the lines. But the big thing is just the number of channels. If we look at the slave CPU here, we can see that it's got I believe it's 48 pins that go around the outside edge. If we're going to monitor what that CPU is up to, or if we're going to monitor what this work RAM is up to, we need a lot more than 8 channels. We need to be able to read, you know, in the case of the work RAM, we need to be able to read 40 channels at once. Same thing if we want to be able to read what's going on with this EEPROM. If we want to see all the signals simultaneously, we need something that's going to handle at least 40 channels. So that's where these systems have a big advantage over those modern inexpensive USB logic analyzers. Is these HP systems were designed, basically it's what they were used to develop this console hardware in the first place, and so they, depending on the unit you get, they have the capacity to handle you know, over 100 lines at once. But what's even more important than being able to handle so many lines at once is actually being able to decode what's going on with them. If you just hook up a bare bones logic analyzer, all it's going to show you is the 0-1 pulsing pattern, you know. What's cool about these HP analyzers from the 90s is they have what's called an inverse assembler, and the inverse assembler goes through and decodes basically what a raw assembly language is executing on the CPU. It's able to read all the CPU lines simultaneously, and then it basically is able to reverse assemble it and say, you know, this instruction is executing, or this line of memory is being written. And so knowing that, we can, you have to have some knowledge of 68,000 assembly language. Big shout out here to Leo Oliveira, I believe is how you pronounce his last name. I apologize if I'm mangling that, but Leo Oliveira has been helping me decode the assembly language that I've been reading off this bad Sega CD. And basically, if you can figure out where the code is crashing, then that tells you what part you need to look at to repair. So, okay, enough talk. Let's go ahead and take a look at how this works. Okay, so I've started up the analyzer here. This is its startup screen. So HP sells a whole bunch of, actually I should say HP was HP on these units for a while. Then they spun out to a different company named Agilent, and now there's renamed themselves again to another company called Keystone, I believe. Doesn't matter much for our purposes. All I need to know is you're looking for, if you're interested in doing this, you want to get an HP, something in the 16500 series or something in the 16700 series, generally speaking, although there's a few other models that'll work as well. If you Google HP inverse assembler, you'll find not only the files to make it work, but also some documentation on the files that you would load onto the unit to make it work. So yeah, let's talk about this. So these large units, like the 16500, 16700 series, there's 5 expansion bays inside, and those expansion bays can have a logic analyzer. In this case, this has 2 analyzers inside of there, and they also can have an oscilloscope. This also has 2 oscilloscopes inside of it. It also can have pattern generators, other kind of electronic stuff. But if you decide to go shopping for one of these for yourself, make sure you get one that still has expansion cards inside of it, not one that's been gutted out. There's a lot, usually the inexpensive ones have had those boards removed. They're usually not too expensive. I got this 16500C for $150 plus $50 shipped with all the cards and cabling, so that was actually a pretty good deal. Later on I might step up to a 16700. I've seen those go for about maybe $400 or $500. It's just a little faster and a little bit more modern, with a bigger screen than this one, but for just getting started, you know, this unit does fine. So these use floppy disks. I have a USB floppy drive somewhere over here, buried under all my paperwork. Yeah, so I have a floppy drive, and so what I did was I just went and Googled the HP inverse assembler files and loaded them onto this floppy disk, and then there's a hard drive inside of here where you can copy the files. The hard drive will also let you save the data that you go and read off of the CPU. So this particular HP unit that I bought's got two logic analyzers. You know, in this case you'd see it's rated for 110 megahertz or 500 megahertz, depending on how many samples how many lines you're using. You know, Genesis runs at 7 megahertz on the CPU, so 110 is more than enough for this and probably any other retro platform. The Genesis uses a 68,000, Motorola 68,000 CPU, so that's going to be the inverse assembler program we're going to use, but there are also inverse assembler files for other common console processors like a Z80 or a 6809. So again, you know, one of these vintage era 90s HP analyzers are perfect for working on retro console hardware. So let's talk about the probe lines that come out. So in this case, there's two analyzer cards. Each analyzer card has 4 lines coming out of it. I only have one hooked up right now. There's 4 lines coming out, and I'm not using this one, but each one's labeled Pod 1 to Pod 4. You can see we've got Pod 1 and Pod 4 right there, and 2 is underneath. And each of them has 15 signal lines. You can see, or 16, sorry, 0 to 16, plus a ground and a clock line there on the end. And so, and by the way, these are all called floating probes. I guess they call them that because you can hook them up wherever you like. But you see each one's got a color-coded tag, so you know, number 2 is red, and 3 is orange, 4 is yellow, and the other end of the wire has a corresponding tag and a corresponding number. And each of them, probe lines, has one of these little grabbers on the end. I don't know if you'll be able to see. It'll focus on that. You see there's little metal, basically when you squeeze the grabber, a little metal grippers come out of the end there, and you can fasten that around the pin. And that's how the lines hook up to the CPU and stay in place. Okay, so big question is, how do you know which probes go where on the CPU? That's where you go and check the manual for the HP Inverse Assembler. You can see that we've got, here's their list of when you're connecting directly to the 68000 or 68010 with logic analyzer probes. The list of these pods, you've got pod, this column is pod numbers, you know, pods 1, 2, and 3, the bit number on each pod. So if we look at pod 1, bit 0, that's going to correspond to number 1, bit 0 on here. So pod 1, bit 0 is a data line, and it's going to go to D0 on the CPU. So we have this schematic of the 68000's CPU, and if we look at D0, it is right here at the top. It is pin number 5 on the CPU. So what I did was I went through and wrote down I basically matched all these up and wrote them all down on here, so I wasn't going to have to keep going back and forth to checking back and forth against this sheet. So anyway, that's how you figure out which lines go where. Okay, so let's talk about the logic analyzer setup. So this has 2 logic analyzer boards inside of it. Each one's got 4 cables. I've only got one hooked up right now. I've got the other set of 4 cables here in a bag. Theoretically, if I wanted to really go crazy with probes and cabling, I could hook up the second logic analyzer and monitor both boards at the same time. Not going to be doing that, just too much to deal with. This is already enough. Okay, let's go over how you set up this particular analyzer. I think the steps are pretty much the same for all of the 16500 series. I know there's 16500 A, B, and C, and the process is the same for them. It's different for the other analyzers. You have to check the manual on those. So what we're going to do is we want to load the inverse assembler for the 68000 from the hard drive. So I'm going to go to configuration, hard disk, and it's going to take a minute to read. Okay, here's a list of all the files I've got on the drive, and if we go down to right here, first there's a configuration file that we need to load for the probes. Just so you can see some of the buttons here, this defaults to load, but if we wanted to, we could rename the file, copy it somewhere else, format the hard drive. We're not going to do that. But in this case, we're going to load, and you know, there is one trick to this. So if we go to load this configuration, it gives you an error, no configurations loaded, and it turns out it's because we're trying to load that probe configuration to all the boards inside the analyzer, including the oscilloscope, that it's not valid for. So instead, we need to tap up here on all, and rather than doing it to everything, it's only going to go to the logic analyzer. So we'll pick that, hit execute again. Okay, and then we get a message that says unable to map all clock specifications. It says that because of little differences with this type of analyzer, this is important. 1 goes to A1, 2 goes to A2, 3 goes to A4. And what they mean by that is that those are references to the pod numbers. Anything on our matchup sheet here, which says where our pins go, anything for that says pod 1 on the instructions will go to the first pod coming out of the back. Same thing for pod 2, but pod 3 actually goes to number 4. So that is why over here I am using pod 4 for those connections, and pod 3 is just empty. That tripped me up the first time. I used pod 3 because it said pod 3 on the instructions. Wasn't working correctly, and this is the reason why. So, funny little thing there, easy to work around. Okay, so once we've loaded the probe configuration, then we need to go down and load the inverse assembler itself. Come down here to 68,000 inverse analyzer, or inverse assembler for the probes. Notice also we can do a Z80, for example. Like I said, there are other types of processors, but we just want 68,000, so we'll execute that and we're good to go. So now we'll go ahead and go back to the configuration and we'll switch over to the logic analyzer. Okay, this is the opening screen of the analyzer where basically you assign which cables are going to do what. So in this case we've got the 4 pods for the first analyzer. If I had the other 4 hooked up for the second analyzer, I could do something with them. So in this case we're only going to deal with one CPU at a time, so there they are. It's already set them up and mapped them for us. So now we'll go to the format. Okay, so if we didn't have this pre-configuration, we could go through and label how the lines are assigned, basically one line at a time. In this case, HP has done all the work for us with the 68,000 inverse assembler, so you can see that it's went ahead and labeled some of the address lines, the data lines, stats lines, and size, the size of memory it's getting moved around, and VMA, which I'm not quite sure what that is. But if we go ahead and scroll over here, we can see that pod 1 has our data lines assigned to it. That's what the stars are. Pod 2 has our address lines assigned to it. Pod 3 is empty, because weirdness. But then pod 4 has some more address lines, our status lines, and the size, and VMA. Now, one other thing that's important here is, let's see, where is it at? Where's our clock lines? Here we go. Okay, so there's also clock lines. Total of 4 available clocks since we've got 4 probes out. In this case, we really only care about 2. If we look on the sheet, there's 2 clocks down here at the bottom. We're going to use the clock line off pod 1 and the clock line off pod 2. And so those are hooked up here, and they'll be under A and B. So now, let's see how this goes. I've got Shaq Fu in here right now as a test game. I'm going to go ahead and turn that on. And there's our startup screen for a Genesis cartridge. Okay. Now, if we come over here and look, you'll see that it's showing indicators that show that activity is occurring on those lines. So we've got our clock signals are lighting up and down. We've got signals here on pod 4. If I scroll over, again, we've got those up-down signals showing that everything is hooked up. keep in mind that only shows you that you've got the pins wired up. If one of these wasn't showing any activity, then it would show that maybe that probe had popped loose off the board and it has to be reconnected. In this case, I've got everything hooked up. It doesn't tell you if you got two probes flipped around backwards, though. The only way you'd know that would be if the assembly language that it shows you is invalid or showing bad addresses or something like that. So you have to be careful to double check that you've got everything wired up right. So let's go ahead and take a sample. Oh, actually, sorry, before we do that, let's talk about triggers. So triggers, I need to learn a lot more about them. They're very powerful. You can do a lot more with them. Basically, what the trigger does is you're basically saying you can set up a specific state and say whenever this state happens, capture it. And that means, like, for example, if there's a specific memory address you're looking for, you could assign that, you know, over here in the address, and as soon as it saw that, it would take a snapshot and you'd be able to see all the assembly language code that happened before that it hit that line, that address that you were triggering for. Same thing for a particular piece of data, or if there was a particular type of, you know, 68,000 operation that you were trying to trigger on, you can do that. Oh, whoops, I did not mean to set that. We're going to go back up to absolute. Basically means anything. I'm doing this wrong. Oh, no, I'm going to have to clear this. Clear. Done. Done. There we go. Okay. And then if we scroll down to the bottom, let me switch to terms. Scroll down to the bottom. You can also set it to trigger on a specific memory range, so you could have it, you know, trigger whenever some range of memory is written or read. Or you can set a timer, which is what we're going to do here. So we're going to say that we want to get 2 seconds of data. Whoops. Okay, 2 seconds of data, and we don't want to deal with more than that because it starts to be too much. And you can set up multiple redundant triggers. You can, you know, say if it's this or this, then trigger, or go to that. You know, you can get pretty complex with them, but we're not going to in this case. Okay, so let's go ahead and do a capture. I'm going to go to the listing here. It's showing blank. We haven't captured anything yet. So let's go ahead and turn this off. And so I'm going to go ahead and hit run here, and normally it would capture 2 seconds of assembly language code, but in this case it says there's a missing clock, and that is because the system's off. It's not reading a clock signal from the board it's hooked up to right now. So it won't start counting. It only captures 2 seconds of data if it can grab 2 seconds of data. So right now it's not capturing anything. If I go ahead and kick this on now, there's our startup message. And if we come back now, we can see that we've captured 2 seconds of assembly language data. And let's actually just scroll down through it. We need to just tap on that first. And so, since this is just the TMSS startup, there's not too much going on, but we can see that it's doing some memory operations, and then it's starting to issue some CPU instructions right there, and there's another one there. Okay, so now we're going to do the same process again, but with the Sega CD boot. So I've taken out the cartridge, and I'm going to go ahead and tell it to start again. So now it's waiting for data, and we'll go ahead and turn that on. Don't have anything showing on the screen, and we can see over here we got our dump. So we can see that it was starting to read some data, again off the ROM. That's going to be the all BIOS data. Now, like I said, it would take a while to scroll through this manually, but what I'm going to want to do is I'm going to want to dump this to the hard drive and then I'll copy it over to the computer later to look at it. So I'm going to go back to the system here, and then I'm going to go to the hard disk, and then what we want to do is we want to store the current sample memory, and let's see, I've got a little directory to store this stuff in. I made a Sega CD directory, so we're going to change directory, and then so we're going to store what's currently on the logic analyzer. I'm going to call this bad 1 for our first bad dump, and then I'm going to execute that, continue. And it's going to ask, do we want to store the setup and the data, or setup only? We don't care as much about the setup because that all came from the HP inverse assembler for us, so we're going to store the setup and the data. It's the data we care about. And it takes a moment. You can see it is dumping the file. Alright, so it is going to dump this. I am going to do probably 2 or 3 more captures the same way, and then I will transfer the files over to my laptop and compare that to the same BIOS code running on an emulator and see what I can figure out from there. So that's the end of this video for now. I'll do some more investigation, and hopefully we'll find out that this unit can be salvaged somehow. To be continued.